So, in the blue, the d orbital set, how many atomic orbitals do we have? 5. 5 atomic orbitals. How many can each atomic orbital hold? 2. And how many total electrons can be in the d orbital set? 10. Okay? And then the last orbital set is F. How many orbitals are in the last orbital set? 7. How many total electrons can be contained in the F orbitals? 14. So, M sub L. This quantum number identifies, it doesn't describe, it identifies a specific orbital within the orbital set. So let's say that my last electron goes into this set of orbitals and it happens to be in a p orbital. I don't know which p orbital that's going to be in, but it goes in a very specific one. So the M sub L value identifies the specific atomic orbital it goes into within that orbital set. We must identify N, our energy level, first. Then we identify L, our orbital set, and then M sub L defines the specific orbital within the orbital set. So I'm going to go ahead and put the numbers on here. Remember these little numbers I said we'd talk about later? All these little ones next to the letters? We're going to put them on this periodic table. Okay? M sub L is always 0 for S. There's only one orbital there. There's nowhere else you can go. The value is 0. And I want to point out, if you look down the middle of every one of these sets, what's the little number? 0. Okay, so I'm going to start with D because I think that's the easiest one to see. The pattern. Okay? So what's the first little number by that D? -2. So I'm going to go over here. Remember I said this is 5 orbitals, and oh my gosh, how many rows do we have here? How many columns do we have here? 10, because we can hold a total of 10 electrons. Here's how they go in. The first column, so right above scandium, -2. Right above titanium, -1. Right above vanadium, 0. What do you think comes next? 1. Then what? Then what? Then what? And so on and so forth. Just repeats itself. So it starts at -2, goes all the way through, and then comes back to -2 and goes all the way through again. Isn't that weird? Not impressed? I don't know what to do to impress you guys.
That's D.
That's D, right? L equals 2 is our d orbital set. That's the M sub L values. So let's look at the M sub L values for P. What are the values over here? -1, 0, 1. Can you place them? Over boron, what am I going to put? -1 over carbon. Next. Then. Next. This one, I put it on the side here, but it should be over. Helium is not included in that. Remember we talked about that yesterday. Helium really is over here. So this one should be really, I'm going to put it in that box right there. That's really ugly. So, okay. How do I feel about that? Good? Uncomfortable? Good and uncomfortable? Not good? We love it? Feel like that's what you're doing because you're right behind Lauren? Okay. I mean, yesterday you didn't trust me, so I don't know how you feel. Whatever. How about F? Now, for those of you that I just gave a periodic table to, lanthanum and actinium down here, in those bottom 2 rows, they should not be in the bottom 2 rows. They should be up in that empty space in the main table.
What is it?
That's not for you guys. That's just for these guys that I just gave a periodic table to. Yeah, so just like that. They should be in the main table, not down at the bottom. So if you want to draw them in that empty space, I would encourage you to do that. So down here in F, what am I going to start with?
-3.
You got it figured out. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Negative 3, negative 2, negative 1, 0, 1, 2, 3. And then S, what's the only value we have for S? 0. So M sub L is 0 for both of those. And I'm going to label at the top, M sub L is in maroon, because everything else is in purple or dark blue. Okay? Because I put all those numbers in this color. But I don't want to write M sub L for all those numbers. You good with that? You don't want to talk to me? Fine, whatever, it's fine. That leaves the last quantum number. Oh. Spin. Spin only has 2 values.
Wait, so how many electrons can you have?
6.
But S doesn't have any.
S has 2. Yep. So, the spin quantum number can only have 2 values. It can be positive 1/2, which means spin up. It can be negative 1/2, which means spin down. And the only difference between spin up and spin down is the direction in which they spin. Okay, so they're spinning opposite of each other. And we just say that it spins in a certain direction, then it's up. It spins in the opposite direction, it's down. So it can only have 2 values. No 2 electrons can have an identical set of quantum numbers. So the spin is what causes the set of numbers to be different. With just the first 3 quantum numbers defined, we have 2 elements that have the same quantum numbers. Once we define spin, we can pinpoint specifically which element that is. So, I'm going to tell you that the first half of the M sub L values is positive 1/2, and the second set of the M sub L numbers is negative 1/2. Oh my gosh. So what that means is that we wrote those numbers twice. Hello? That's right. I just post the link in my classroom, and I haven't had anybody say anything. I think I made it available to Riverside so that they can view them, but that's the only one I made. I mean, I don't want everybody to benefit from my wonderful knowledge. Yeah. Yep, bye. Okay, YouTube. I'm older than that person, and I figured out. I don't know. I must be doing pretty well then. Okay, so we wrote these sets of numbers twice. The first set is positive 1/2. So if I look at P, this first negative 1, 0, 1, that's positive 1/2. And the second negative 1, 0, 1 is negative 1/2. Same thing with D. From negative 2 to positive, oh, that was terrible. Negative 2 to positive 2, the first set is positive 1/2. The second set is negative 1/2. Down here with F, the first set from negative 3 to positive 3 is positive 1/2. And then the second half of this, negative 3 to positive 3, is negative 1/2. And then finally S. The first column, hydrogen all the way down through francium, is positive 1/2. And the second set, which includes helium, all the way down to radium, is negative 1/2. And there you go, your 4 quantum numbers. So, yes, Gracie. So here. See how there's negative 2 to 3 and there's negative 2 to 3 again? The first set is positive 1/2. The second set is negative. And then the same this -3 goes with this element right here. This -2 goes with this element right here. Okay? And the first half is gonna be positive 1 half, the second half will be negative 1. So you're
I
gonna
figured it out.
what?
I figured it out.
Okay, Bridget.
So the zeros above the first two columns, are they supposed to be like the periodic table or the?
Those are the Ensabel values for the first two columns, for S. Other questions? My glasses keep fogging up, so I keep playing with them. Yes?
I can't really see the numbers.
Positive 1 half, negative 1 half, yep. Okay. So, you guys are good to go, right? You got it all figured out? I can give you a homework assignment and let you loose. Wow. Okay, let's do an example. I figured this is all very abstract yet. It doesn't make a whole lot of sense. We need to do an example or two. And let's see if we can get this figured out. Okay. Now, I want to tell you that they always go in the order that we talked about. We talked about them. N, L, M sub L, M sub S. We have to list them in that order. We're going to identify them in that order. It is very important. And we are going to let's see. Connect that to the Bohr model. And I think that'll be good. So what I want you to do, the first thing I want you to do, this is for lithium. I want you to draw the Bohr model for lithium. I think if we start with the Bohr model, that'll make it a little easier. So draw the Bohr model for lithium. Lithium is element number 3. So draw the Bohr model for lithium, and let's see where that gets us. My mouse is over there, so I'm trying to find my mouse to read my email. What side is that? Nuts.
Yeah.
Okay, that makes me feel better. Actually, I'm glad. I think. Do we remember how to do the Bohr model? Still working on it? Not sure? Napping? Dreaming of Vicks? Okay. All right. So let's talk about the Bohr model. Do a little quick refresher and make a connection here. Okay? So lithium has 3 protons because its atomic number is 3. It's 3 on the periodic table. That's what it means. It has 3 protons, and we're talking about atoms, so protons and electrons are equal. So we have 3 electrons. How many electrons? We're going to start closest to the nucleus, and this circle in the middle is my nucleus. So how many electrons can I put in that first energy level? 2. Because we can only put 2 electrons maximum in that energy level. Okay? So then, how many electrons do I have left over?
1.
And where's that 1 electron going to go? The next energy level. So here's my 1 electron in that energy level. Now here's the thing about quantum numbers. We can write quantum numbers for every electron in an atom. And while that sounds like a lot of fun, and now I'm starting to think we should write a board game to go along with that, we are only writing the quantum numbers for that last electron. We are only writing quantum numbers for that last electron. Hello? Yeah. Yes. I have to manually enter it. No problem. Bye. So, we are only writing the quantum numbers for that last electron. And if there would be 7 electrons in there, we would just pick whichever one would be the last electron, and that's the quantum numbers we would write. Okay, so, yes, Chase.
How do we know which one's the last one out of like 7?
We just pick one of them. We're just gonna pick one and say that's the last one. And I think, yeah, in the next example, we can talk about that more if that still doesn't make sense. So I need to write my quantum numbers for that one electron right there. That's called our valence electron. It's the last electron, or it's in the valence shell, the outermost shell that contains electrons. That's a valence electron. Okay? And I'm gonna write my quantum numbers in this order. N, L, M sub L, M sub S. Always in that order. N, L, M sub L, M sub S. So the periodic table that you took notes on, I want you to find lithium. This is good. I hope this blows your mind. You haven't been excited about anything all year yet. We're almost at interims. This should make you excited. Hint, hint. Okay. So what's the N value there?
2.
Okay. What's the L value?
0.
What's the M sub L value?
0.
And what's the M sub S value? Done. The Bohr's model is not the accurate model of the atom, but we use it as a teaching tool because it's got some aspects of it that are correct. Okay? But that's not what the atom looks like. It's not like have you ever seen those jawbreakers where you put them in your mouth and they're like green when you put it in your mouth and you suck on it for a while and then you take it out of your mouth and it's red and you put it back in your mouth and you suck on it for a little while longer, you pull it out and it's yellow, right? That's what this model reminds me of, is a jawbreaker. That's not what it really looks like. But this is a great teaching tool for us because there are aspects of it that are very correct. And there are aspects of it that are wrong, but it does a good job of representing the atom. So what do we think? How do we feel? Fair?
So you guys probably covered this yesterday, but how do you determine the M sub L and the M sub S value?
That's what I'm.
Yeah, so M sub L values, those are the ones that we wrote down today, right? Those are the ones that are in maroon. So I found lithium, and I went up to the maroon that I wrote above the columns, and that's the value. And then M sub S I wrote in green, so I just pulled those numbers off there.
So the maroon is just the 2 zeros right here,
Yes.
and then the MS is the negative, or the.
Positive 1/2 or negative 1/2. Okay, so how do we feel? Should we try another one without making you feel better? Because you're still not excited, and I'm very upset. If it was Tuesday, you'd be able to tell. Okay, so let's try another one. I'm just going to erase my stuff here. Okay. I mean, it literally just changed the element. Which one are we looking for? Aluminum.
Where?
Does it bother you that I did this in blue instead of red? Oops. What number is aluminum?
13.
13. So go ahead and draw your Bohr model. Yeah. So the valence shell here has 3 electrons in it, and it doesn't matter which one you pick, but we're going to pick one of those 3, and we're going to do the quantum numbers for that one. We're going to call it, that's the last one that went in, and that's what we're going to write the quantum numbers know, but we're writing this for the last one that goes in there, so I'm just gonna draw my dots, and I'm gonna say, this one right here, that's the one we're writing those for, that's the last electron that went in. Yes?
Okay, so another one, there was a way to figure out how many electrons are in the last one.
Yeah, so remember, aluminum, you put your finger on aluminum, it's in the third row. So it's gotta have 3 rings with electrons in it.
Okay, because there's a row.
And then the column, if you ignore that middle D block, how many columns do you count over? 3. There are 3 electrons in the last shell. Okay? Yes, Sierra?
I'm confused on how, like, the quantum numbers for the electrons could be different because it's all for aluminum and that's what we're looking at on the third table. So how is it specific for the electrons?
That's a good question.
And I think you're not gonna answer it.
Not yet.
Okay.
Not yet. Yes, Gracie?
How do you know what?
It's how many rows there are. So aluminum is here. 1, 2, 3. Yeah, you can draw as many rings as you want, but only 3 of them are gonna have electrons. Okay? Chase, did you have a question? Oh, did somebody else? Oh, Carly?
What's a good way to remember the maximum number of electrons per ring?
I wouldn't remember them. I'm gonna explain to you why it's like that at some point. Okay?
What's that?
I can do it after this if you want me to. Yes. Oh, wait.
You want us to draw the 3 on the last one, or?
No, you don't have to do that. I did it because I'm just saying we're just gonna pick one and we're gonna call that the last one that went in. Okay? Was that your question, Trini? Okay, go ahead.
So I don't know if I missed it, but so like right here, with this just carries through, so that's 1 for the N value, and then that's 2.
Yes, for the main group, only the main group. Those are different, they're shifted down one, okay? Any other questions before we do this one? Okay, so I want you to find aluminum on the periodic table. You got it?
Yeah.
What's the N value?
3.
3, okay. N equals 3. Does everybody see where that came from? What's the L value? What is it? 1. Does everybody see where that came from?
Yes.
Aluminum is in the P block. Right here? And in this entire block, L equals 1. So for any element that's in this block, except for helium, because helium really belongs over here, every element that's in this block, the L value will be 1. Okay? The M sub L value. I hear -1. -1. Does everybody see where that came from? Okay, so if we go up from aluminum, the value here is -1, so that's where that comes from. And then the M sub S value. +1/2, because these first 3 columns correspond to an upspin. Okay, so these are the 4 quantum numbers for that last electron. You guys are impossible to impress.
I think this is probably the easiest thing.
This makes sense, like this stuff.
It makes sense?
Yeah.
Yeah.
I gotta work harder. Zach?
I'm just confused about helium, like how that whole thing.
Hydrogen and helium are funky because they only have 2 electrons and they follow the duet rule. So there's only 2 electrons in that valence shell. And that's all I'm gonna say about that. That kind of goes along with Sierra's question about the different electrons in these specific elements. Okay? We'll talk about it more when we get a little more knowledge. Owen?
Is it possible for like, that would get an example or whatever of aluminum being, what is it, M sub S? Having a value of like -1/2?
Nope. Nope. And the next thing that we're gonna learn are electron configurations, and we're gonna see why it's positive for some of them and negative for the others. And it's very specific how that happens. Okay? Chase?
So we found all these numbers, but like, what are we doing? Like,
Oh, what do they do?
why did we learn, like, I don't understand. It just doesn't make sense to me.
You don't understand why we learned it?
What we're
'Cause-
doing with it.
That's an address. So fine, if you really wanna go there. Do you remember this paper here?
Yes.
Do you see down here at the bottom where it says quantum mechanics? And then do you see this list of things A through F that's only got 4 numbers with it? For
You can name the element.
quantum numbers? So let's do one of these. This doesn't go with this slide, but let's do one of these. I'll write it up here so you don't have to dig out your paper if you don't want to. But this is A. Actually, let's do C. So this is what C is. 5, comma 3, comma 0, comma negative 1/2. And those 4 numbers are in the correct order. They're always going to be N, L, M sub L, M sub S. Always. Okay? So when the N value is, like, we're trying to identify which element this is for. So we have all 118 elements on our periodic table that we need to pick from. Lauren?
So when it's like 5, we have like multiple rows that equal 5.
That's correct. That's tricky-ish. Okay? So we're trying to narrow this down from all the elements on the periodic table down to a single element that this describes its last electron, its valence electron. So Lauren said that in energy level 5, right, it's going to be the 5th row, kind of, but then, so you have the 8 elements from S and P, you have these 2 right here in energy level 5, and you have these 6 over here that are in energy level 5, but then you have these 10 in D that are in energy level 5, and then you have these 14 down here in F that are in energy level 5. So we've narrowed it down from 118 elements to 32. Now, Carly, you asked me about how to figure out, or how to remember, the order of the electrons that go into the rings. Well, we just talked about energy level 5, and there are 32 elements. I don't know, just.
Oh my goodness.
I'm confused.
Look, energy level 1, there's 2. And then
What?
there's energy has 2, and energy level 2, there's, never mind. That doesn't make sense. What goes in energy level 2? 8? Oh, then it does work. What? That was the only thing you said all year.
Okay. And aside, just really quickly. 2, 8, 18, 32, 32, 18, 18. In energy level 1, there are 2 elements.
Oh my
We can only have 2 electrons. In energy level 2, there are 8 elements, and we can only have 8 electrons. In energy level 3, we have these 8 plus these 10. 18. Finally! Do you guys just hear that? She said her mind is blown. Finally! Okay. 18 in energy level 3. In energy level 4, we have these 8, these 10, and these 18. That's a total of 32. Energy level 5, 2 plus 6 is 8, plus 10 is 18, plus 14 is 32. Energy level 6, 2 plus 6 plus 10 is 18. Energy level 7, 2 plus these 6. Wait a minute.
So it doesn't make
But we stopped there because we don't have any more elements. We ran out. But theoretically, it could have 32 and maybe even more. But we don't know because those elements don't exist yet. Do you see the connection? Okay. Back to these quantum numbers. It is all connected. Trust me. Let's go back to these quantum numbers. So, Ally said there are Lauren said that there are multiple places that you can have 5, energy level 5. How do we know which one it is?
The next one, I just figured it out.
L is 3. Where is L3? In the F. So now we've narrowed it down from 32 to 14. Right? So the element that those quantum numbers describe are somewhere in this energy level, or in this row right here, in those 14 elements. Now we need an m sub L value of 0. How many elements in that bottom row have an m sub L value of 0? 2. The last quantum number is -1/2. So which element is it? Fermium. So now here's what I'm going to say. Is that important for you? No. What's important here are the connections that we're making. Because all this information came out of the periodic table after Henry Moseley reoriented it so it's based on atomic number. These patterns just fall out of the periodic table. Okay? We're going to continue to come back to this over and over and over again. We have one more. Two more. It's really 1.5. It's one major idea and then a baby idea. And we're done with this unit. Okay? So what I'm going to do, what time is this class over? 05. Do I ask that every day? Will I ask it every day for the rest of the year? Okay, just as long as we're on the same page. What I'm going to do is stop here, and I'm going to give you an assignment from this paper. I'm going to give you an assignment. I'm not going to give you an assignment tonight. I'm going to give you an assignment tomorrow from this paper because we need a little more information. Now, tomorrow I'm going to cover electron configurations. Tomorrow I'm going to cover electron configurations, and then that's the next big idea. Electron configurations. And we're going to connect Bohr models, quantum numbers, electron configurations, and hopefully at some point you're going to get like, oh my gosh, this all fits together. You'll understand why we have these numbers here. You'll understand why we have +1/2 for some of them, -1/2 for some of the others. And that will get us to next week. We'll do a baby idea on Monday, test on Thursday. Oh, goodness gracious.
Mrs. Fowler, will we have to memorize the quantum numbers?
I am exhausted. Will you have to memorize what?
Quantum numbers.
Yes.